Hi and welcome back. Today we'll talk about skeletal muscle mechanics, which is the next logical topic after you learn about basic muscle physiology and sliding filament theory, which you now know is the theory behind muscle contraction. In particular, today we'll talk about force-length relationship, which is just a relationship describing the force generated by your muscle and the length of the muscle itself. I will describe the differences of this relationship for isometric contraction, or just static postures, and continuous movement. And then I'll give you formulas describing these relationships that are very useful in clinical and research settings. Let's get started. Simple things first. We'll first talk about isometric contraction. So there is a plot here and there are axes. What are these axes? So the vertical axis denotes normalized muscle forces, you can see, right? So that simply means we'll be plotting muscle forces along that axis. But why are they normalized, you may ask? Well, that's simply because we want to study force-length relationship across all of the muscle. But the problem is, all of the different muscles generate different forces. So think about lifting a dumbbell with your bicep and then trying to lift the same weight with your pinky flexor. Won't be quite able to do that, right? To account for that, we take all of the forces generated by the muscle and normalize them or divide them by the maximal force that muscle can generate. So that's exactly what you see on this axis. Where at 100%, we have the maximal force we normalized all forces onto, right? So now, if we're studying force length and we're normalizing forces, we also need to normalize the length, right, ideally. So that's why on the x-axis, we see normalized muscle length, right? So now if it was normalized, we start looking for 100% to find a value on which they were normalized. So the value is L0 or L0, also called in the literature optimal fiber length. And what is optimal fiber length? Optimal fiber length is simply a length of your muscle at which this maximal force we just talked about can be reached. So that's that simple. Now, what's the physiology behind this maximal force, or maximal contraction is also called? So you guys remember, every skeletal muscle is composed of these little contractile units called sarcomeres, right? Shown right here. Sarcomeres from the previous lecture has thick filaments, shown in red here, and thin filaments. The interaction between these two is what leads to muscle contraction. Now, what is happening at the optimal fiber length? Simply, at the optimal fiber length, all of the myosin heads of the thick filament, shown in red here, are interacting with all of the actin binding sites of the thin filament, shown in green, right? So if all of the heads are recruited, that is the maximal force you can generate. It's that simple. Now, obviously, if you start stretching the muscle, you're stretching the sarcomeres. And when you're stretching the sarcomeres, what you do is you start pulling the thin filaments away from the thick filament. Now, that means some of the myosin heads will become vacant. So some of them won't be participating in contraction. If some of the myosin heads are not participating, you will be generating suboptimal force. That's why the force starts decreasing here, right? Obviously, if you take this to extreme and you pull the thin filaments away from the thick filaments so that there is no interaction, shown here, you will get no force. Now, this was stretching of the muscle, right? Now let's talk about shortening of the muscle. So we're going below 100%, so below optimal fiber length. So what you start seeing here is, you remember that sarcomere is pretty small itself, but in order to make itself smaller, it starts sliding the thin filaments from the opposite side onto each other. So what does that do? That again reduces the amount of available actin binding sites for those myosin heads to bind to them. If not all of the myosin heads are recruited, that means you're again generating suboptimal force. Now, there are another two factors that are contributing to suboptimal force here. The first one is what we see at the muscle length below 80%, or once again, below 80% of normalized muscle length, or this L0, is the calcium dynamics are changing. In other words, there is not enough calcium released to muscle to work with it. What does that mean? You remember that calcium is needed to bind to troponin, so that troponin starts pulling onto tropomyosin, exposing those actin binding sites for myosin heads to bind to them and start stroking to produce force, right? So at below 80%, we see that not enough calcium is really released. That's why, obviously, if you're not exposing those actin binding sites, not all of the myosin heads can bind to them. So now another factor here is that you actually, when the sarcomere shortens, the thick filament starts being forced against the supportive protein called Z discs, so that also reduces the maximal force that can be generated. Now, all of these dynamics in sarcomeres will lead to a curve shown in blue here. So you'll be able to generate the maximal force in the optimal fiber length, and the force will be reduced at both ends, to the right and to the left, from the optimal muscle length. Now, this is what's called active force-length relationship, because you're actively generating that force. But you also know that if you're exercising in the gym and someone gives you a dumbbell that you cannot potentially lift, or say a barbell, but you somehow still, even if your muscles are really stretched, you somehow still opposing its weight and not allowing it to drop to the ground. So how does that happen? Well, let me draw another curve here. Here's a promised line shown as dashed black line. Let me try to explain it now. So it appears that your muscle tissue will act kind of like an elastic band when you will try to stretch it. So what does that mean for us? That means there will be some passive contribution. So say your muscles are stretched and you're not actively trying to shorten them. There will be some passive contribution or passive force contributing to this force-length relationship. So how does that look on our plot? So that means you will be actively generating force, and then when you will cross some value, there will be passive contribution. And where does the passive contribution start? Passive contribution usually starts at the optimal fiber length. When you start stretching the sarcomere, it starts acting kind of like an elastic band. So now a little bit of terminology for you here. We usually, when we refer to bits of this curve, every bit of this curve has a name. So this bit of the curve, where the curve ascends or increases in value, is just called an ascending limb. So that's simple. Now this bit right here is obviously called descending limb. So you go down, you descend. And then obviously this one is called ascending limb again. Now also a couple of facts I want you to know. There are additional ones, but still. Usually, based on how our muscles attach to our skeleton, you won't observe values of stretch larger than 130% of the optimal fiber length, or 70 or about that percent of the optimal fiber length again. Now you may ask me, how did anybody obtain this curve then, right? Good question. Scientists actually took the muscle, they isolated the muscle, and started either stimulating it with electrical current to shorten it and see how it behaves in here, or started stretching it with some mechanical device to look at how it behaves in here. That's it. It was studied in vitro. Now, what I want you to remember once again, this is a force-length relationship for isometric contraction. Now, we'll talk about something that's not emphasized in textbooks, which is a force-length relationship for continuous movements. There are multiple scientific papers published to answer the question if the force-length relationship for isometric contraction is applicable for continuous movement or a movement you perform during the day. One of these papers was published by Gillard, Yakovenko, Cameron, and Prohaska, where the researchers studied the movement of the wrist, or flexion and extension of the wrist in particular, in order to answer that question. Now, looking at these plots, you might have noticed that we're now looking at the wrist joint angle, which is the excursion of your wrist, and normalized torque. So you may ask me, why is that? We're looking at the muscle length and muscle force. Why are we now switching the modalities? Well, let's look at this together. If you are rotating your wrist, say you're extending your wrist, your extensor muscles that are responsible for extension of your wrist, they're shortening, right? And then if you're flexing your wrist, those muscles are elongating, but the flexors are shortening, right? So now, looking at the excursions of the wrist or joint angles of the wrist, you can judge what's happening with the muscles. Now, normalized torque. Torque, if you remember from physics, is just a rotational analog of the force that is linearly related to the force. So now, looking at the torque, you can judge what's happening with forces, right? So now, let's go to the experiment. During the experiment, researchers asked the participants to set their wrists at the particular angle and start moving from there, either flexing or extending, depending on which curve they were trying to obtain. Now, there were two types of flexion extension. One where you would go and cover full range of motion, or the small ones, about 10 degrees. So if you can see this little hysteresis here, those are denoting the experiments related to the small motion of the wrist, where you would choose the position of the wrist or the angle of the wrist and start flexing from there. Or again, if you choose the position of the wrist and start extending from there. Notice that the x's here are reversed. So here, the upper part of the hysteresis, let's now not look at the lower part, I will explain what that is later. The upper part of the hysteresis should correspond, ideally, to the force-length relationship we obtain here. But you can notice they're different, right? What exactly is different? You can notice that here, there is no descending limb like we described for isometric contraction, right? So for this little short movement, there is no descending limb. And now the same is happening in the extensor muscles. Now, the researchers also decided to study if the same is happening when the wrist goes and flexes or extends at the whole range of motion, right? So now you see that when you do flexion, there is again no descending limb in here in the upper part of the hysteresis. But there is actually a small descending limb when you use your extensor muscles. Now, what does this tell you? This tells you that the isometric force-length relationship, or I should say force-length relationship for isometric contraction, this curve, cannot be really applied for continuous movements because it only matches what is happening in real life only for extensor torque that was accessed to the whole range of motion, not for the little movements and not for the flexor muscles at all. So now, obviously, the main conclusion of the paper that's written here is that the isometric force-length relationship may be not representative of the actual continuous movements. Now, I should also tell you what the lower part of the hysteresis is, right? Because I promise. So ideally, if you would go from the shortened position of the muscle, right, and extend it, ideally, you would expect if you decide to shorten the muscle, it should follow the same force-length path, right? This is not actually what is happening in real life. And the phenomenon responsible for this hysteresis or change in the torque or force produced based on the length or angle studied is called short-range stiffness that is actively studied in academia. Now, let's talk about formulas describing these relationships. Let's first talk about formulas describing force-length relationship for isometric contraction and then move to continuous movements. So all the formulas listed here, I tried to find an original source, but I also listed a couple of additional sources in the description below, in case you're curious. So we usually describe a force-length relationship in two stages. First, active part, and then passive part. You guys remember the active part, we showed it in blue here, and the passive part was shown in dashed black line, right? So the active part, one of the most cited papers describing the active part of force-length relationship was published by Tendon in 2003, where he proposed to model it with Gaussian. This Gaussian takes normalized muscle length that we plotted along the x-axis here, right, using the same notation, takes it as a parameter, and another parameter there is this gamma. Gamma is a scalar of how narrow or wide the Gaussian is. I searched the papers for the values used for gamma, and it's about 0.45 if you want to use it. So another paper published the same year was published by Silva. You can see the equation here is a little bit more bulky, but it pretty much also just takes the normalized muscle length as a parameter and then models the active part of force-length relationship. Now, the second step here, you remember there is also a passive part, right? That elastic stretch or elastic force or passive force that is an answer to the stretch of the muscle. It was also modeled by Fallon in the same paper. And it is pretty much two exponents with some additional parameters. So except for a normalized muscle length, you can see a parameter KPE or a coefficient or a passive element or passive contribution here, right? And this KPE is often set to value about 3. Now there is another parameter, epsilon 0 or epsilon naught here. It's usually set differently for older and younger adults, where it's usually equal to 0.5 for older adults and 0.6 to younger adults. So now let's move to the continuous movements. So one of the first papers that got rid of that descending limb in a force-length relationship that we now know is not really representative of continuous movements was published by Yakovenko in 2004, where he proposed to model active part of force-length relationship with 2 lines. Now, there are 2 conditions in here. So, for the length lesser than L naught or our optimal fiber length, we'll model the relationship by multiplying the normalized muscle length onto this constant. Now, for the values greater than optimal muscle length, so here, we will model relationship multiplying it by a different value. Now, I should say that the A here, the capital A here, is greater than the smaller a, right? So the slope of this guy is greater than the slope of this line right here, right? So this is pretty much how we would model active part to get rid of that descending limb, right? So now you may ask me, what about passive contribution? So because passive contribution is just an elastic contribution of the force opposing the pull, we can actually reuse this equation. So now you may ask me, how will the total relationship look like? It'll be something like this. Now that you know formulas describing both isometric and continuous movements, let's move to the conclusions of the video. So in this video, we started talking about skeletal muscle mechanics and the first mechanical property of the muscle called force-length relationship. We emphasize some of the differences of this relationship for isometric contraction and continuous movement. We concluded that this relationship for isometric contraction is really not representative of what is happening in continuous movements. Finally, we talked about formulas describing both cases that can be used in clinical and research setting. I hope you enjoyed this video. Thank you for watching, and I'll see you in the next one.